All right, so now let's look at number 4B. Again, we're still dealing with hydrates. Now, this is where it gets a little weird. I think over the summer you should have watched this video about hydrates, correct? All right, that's fine. We're going to talk about it now. Sir? I'm not worried about it. It is what it is. I'm tired of dealing with that question. All right, so 4B is a 42.7 gram sample of zinc carbonate times XH2O contains 22.93 grams of zinc carbonate. Determine the hydrate's formula. So what are you essentially solving for? What's the question? Determine the hydrate's formula. How in the world, or what part of the hydrate's formula is missing? Go back and look at it. The water. So what our objective is we're going to do our best to try to figure out what the X is, how many waters we have. Now, here's what I want you to go ahead. Hang on, let me look at this question again. I have too many sheets of paper up here. What did I just do with it? Gotcha. Okay. All right. So, if in the end, this is the common theme, is what we need to eventually get to. We need to be able to figure out the moles of H2O divided by the moles of the anhydrate. This is the ultimate goal. This is where we have to get. And I know what you're thinking. What is that A word? No water. It's been dehydrated. Fantastic. So let's reread the question. It says a 42.7 gram sample of this hydrate contains 22.93 grams of zinc carbonate. So let's think about this. If they tell you that the hydrate is how much? 42.7 grams. And then they tell you that the zinc carbonate is 22.93 grams. Does that make sense? Okay. So, what is the rest of that 42.7? Water. Fantastic. So the rest of this stuff is the water. Now, how did we know? And this is laboratory style question. How would you know how much of the original 42.7 is 22.93 zinc carbonate? What would you have to do to determine that? No. Experimentally. Chemistry of something, of some sort. Not boil it. Boiling is for liquids. Dehydrate it. How do you dehydrate something? You must heat it up. Okay? We're going to talk about these style questions later. We're actually going to look at a specific type of dehydration. This is called that gravimetric analysis. Okay? So we're actually going to take a solid that's a hydrate. We're going to evaporate the water off of it, and we're going to be able to figure out how much water was present in that hydrate. Yes, sir. Yes. All right, so next question. How much is present? Okay. All right, so 19.77 grams. Yeah. Say that again. Oh, you do a subtract. Now, so here's my question. The original goal of this problem was to get to what formula? Based on what I have written, is that possible? It is possible. Okay. We got to get both of these things into moles. Which color in the math part are we not going to use? We're not going to use the black one. That's not, we don't need that. Okay. So here's what we got to do. Why did I do that? Okay. So we've got 18.02 grams in 1 mole. Now, I am going to need your help. Will somebody give me the molar mass of zinc carbonate? All right. Zinc is 65.38. Carbon is 12.01. I really got to get this calculator on my new computer. And then oxygen is 16 times 3. What am I doing? All right, give it to me again. 1 mole. And then, again, like we said, we've got 18.02 grams in 1 mole of water. All right, now, somebody help me out with the moles of zinc carbonate. So 22.93 divided by 125.39. 0.182. 3 if I round it. So 183. Okay, so 183 moles of this stuff. And then somebody help me out with the moles of water. Like it, 1.097. Actually, let's do this. No, we're good because we've got 4 sig figs. So moles. That one actually could be in 4 sig figs as well. Give or take, it's fine. We're just going to roll with it, okay? All right, so here's the next most important part. We've got to now plug these numbers in. So we've got 1.097 moles of H2O divided by 0.183 moles of the anhydrate. You divide. .9. There's no way that's 59. There's no way it's 50. Thank you. So, in fact, if 5.996. Now, doesn't make a difference. It's fine. You're in the thousandths place. So, this is just like empirical formula. This is your 1-9 rule. The tenths place must be a 1 or a 9 or a 0 to round. So what is that going to be? 6. Okay, just making sure we're on the same page here. That's fine. This is 6. So how many waters are in this formula? 6. So really, the only thing you guys need to know of how to do hydrates is that thing right there. If you don't know that, you're kind of screwed. That, very good question. That's a great question. We're trying to determine how many waters are present in the compound. True or false? True. That is the number of waters. So let's rewrite it then. So it would be zinc. I don't like that. Come back. Forward, here, here. So zinc carbonate dot 6 H2O. So this would be your new hydrated completed. Now, throwing this out there, the name of this thing would be zinc carbonate what? Hexahydrate. Cool? So that now makes sense. So again, that is what's kind of weird about this problem is that you have this thing going on that you got to determine the number of waters. And this moles of water over moles of anhydrate is your formula. I'm giving you tools to think through. Let's pretend that you say, okay, I know it's moles of water and moles of anhydrate. I know that I got to do some subtraction stuff, but I can't remember the formula setup. If you had the top thing circled in black flipped, what would your answer have come out as? If you take the red and blue number and you flip it over, it would have been a decimal. You can't have that, right? You've got to have a whole number. So if you did that, you need to make sure your number comes out as a number greater than 1. So flip it over, and that should give you your right answer. Dustin. Yes. Okay, that's a great question. Let's look at it from this perspective. Would you all agree that if we had zinc carbonate solid, it would be in a crystal lattice form? Okay, it's going to be a crystal lattice formation because it's an ionic compound. Yes, sir. Okay. You don't want to hang out for another 30 minutes? Okay. All right. So what does it mean to be a hexahydrate? Thus, this is a good question. When we have a hydrate, that means it has water in the compound, right? So really, in a weird, strange, odd way, that's 6. We've got water surrounding this thing like this. Okay, that's what it means. So every zinc carbonate, for every one zinc carbonate, there are 6 water molecules surrounding the math. Okay? Oh, it depends upon the compound and how much water it absorbs. Is how much water it can absorb. Now, obviously, if you catch it at different times, like South Alabama is really humid, right? So bottles naturally or compounds in plastic bottles will naturally tend to, if they're absorbent, hydrate themselves. That's not a good thing. We don't. You can buy hydrated stuff. It preserves it a little bit longer because it protects it. But naturally, it will hydrate itself if there's a very high humidity. You go to a place where there's no humidity, it won't hydrate itself. But, and again, it can get up higher and higher and higher the more absorbed, but there's a maximum point. Now, every compound has its maximum point, and I have no idea what that is, and we will never get anywhere near that. Yes. Exactly. Yes. Yes. Yes, that's exactly the same compound. But instead of it being in ion form, it's in crystal lattice form. It's a actual crystal that it's surrounding. Okay. All right. So that goes with that. So what I'm going to do, Madison, if you'll take one past one and just pass them across and pass them back. What you're fixing to see is I'm going to take a second. I'm going to pause the video and I'm going to pull my flash. I'm going to email myself something. All right. So let's look at. Again, here's the cool part about this. You know, if you ever get something from me and it has a year on it, that year means that this has been a former AP chemistry exam question. So this question was in year 2000. Now, I'm going to be honest with you. This question has been chopped to pieces. I've taken pieces and parts out of it. This is a revamp. I was going to actually give you the actual question, but I've just pulled the pieces out that are most important to us. Okay, so just kind of keep that in mind as we go through this. So these are these type of questions you may see on the exam. So answer the following questions about BeC2O4 and its hydrate. Does anybody know what the name of the polyatomic of C2O4 is? You should. You took a quiz on it. Oxalate. So this is what? Beryllium oxalate and its hydrate. So calculate the mass percent. Now, this is important. I want you to underline this word. Of carbon in the hydrated form of the solid that has the formula BeC2O4 trihydrate. Now, so the first issue that we're going to run into, what is the question? The mass percent of carbon. Anytime you see that P word, percent, you know that it is what? Okay? Is P over whole. Now, what is the whole thing? And what are we trying to find the percent of? Carbon. Would you agree with that? Okay. Now, here's the easy question. Mass percent of this beryllium oxalate trihydrate. How much of the total mass will be carbon? Say it again. Fantastic. Watch. You're wrong. You said 14. That's wrong. There are 2 carbons, and every 1 carbon is how much? Okay. So we know that this is 24.02 grams of carbon. Now, the difficult part is finding the rest of that junk. Now, so 24.02 times 16 times 4 plus the mass of beryllium, which is something. Yeah, 9.01. Then times the 3 waters. It is. So you should come out with 151.08. It's over there. Shut up. Give me the percent. Thank you. 16%. Now, so my basic question is if you ever see a percent question, please do not miss it. They are way too simple. Hypothetically, what if the question was, what is the mass percent of water in the hydrated form? What's the only, well, other than the answer, obviously, what part of this would change? It'd be the H2O. Okay? It would be whatever the mass of water is, which is 18.02 times what? 3, and you'd plug that number in on top. What if the question was, what is the percent of beryllium in this hydrate? It'd be the mass of beryllium, which is 9.01 divided by the total mass, which is going to be really small, right? Exactly. That's why you could do that way. Okay? All right, B. When heated to 220 degrees Celsius, the beryllium oxalate trihydrate dehydrates completely as beryllium oxalate trihydrate into beryllium oxalate solid plus 3 waters. Now, one thing I want to point out, just reaction style, what do you notice the state of matter of the water is as a product? It's a gas. So will it still be present anywhere around that solid? It's going to be boiled off. So will it determine any mass of that? No, because it's gone. It's out of there. It's flown the coop. So if 3.21 grams of the hydrate is heated, calculate the mass of the beryllium carbonate form. So let me ask you something. Simple question. If we do not do this, but I'm just saying, would you agree that this thing right here is a reactant? Would you agree that this thing right here is a product? So are we essentially just going from a reactant to a product? You're just going from one side to the other. What do you have to do to go from one side to the other? You got to stoich it up, right? Okay, you got to stoich it up. So it's really simple. So we're going to do 3.21 grams, and I'm just going to write the word HYD. What does that stand for? Because I'm not writing that whole hydrate out. I'm way too lazy for that. Now, we've got the grams of the hydrate on bottom, and we need to go to the moles of the hydrate. Now, the great news is do we already have the whole mass of that hydrate? Yes. What is it? Okay, so we've got 151.08 in 1 mole. What's my next step? Can y'all see that, or is that too small? It's a great question. Let's go back. If 3.21 grams, okay? And we said it was 151.08 grams of the hydrate is in 1 mole of the hydrate. Now, we know that moles of the hydrate's on bottom. We got to get rid of what's on top. Okay? Very good. The moles of the BeC2O4, the beryllium oxalate. Why can we not stop there? It asks you about grams. So we got to go to grams of BeC2O4. We know that is 1. What is your mole to mole ratio, and where does it come from? Coefficients. What is it? 1 to 1. So we've got a 1 here and a 1 here. I'm going to help you out with the mass. The mass of it's 97.03. So we got that right there. Okay. So when you do this, your final answer should be 2.06 grams of beryllium oxalate. Now, I'm going to show you an alternative version to this. I normally don't like showing alternative versions because I don't want to confuse you. However, I think it's important that that it can be done from a different perspective if you prefer different perspectives. You okay with that idea? Okay, so here's the deal. And I'm just going to write it and see if you can follow it. Does that make sense? No. And that's why I don't like teaching it this way. Stoichiometry always works. And here's why. Yeah, this is cool if you've already found a percent, right? Okay. But you may not always necessarily have to find a percent. But it does work. So you got part over whole, you got the percent, and of that 3.21 grams, 64% of it is the beryllium oxalate. So it'll work if you want to do it this way. I'm just not a big fan of it. I'd rather do what I know how to do it. Well, really what you need, if you think about it, all you need is the entire mass of the compound, the part mass, and then you just, whatever that percent is, multiply it times the original mass. Yes. Bingo. That would be a lot more convenient. And see, some people see that and say, that looks like less steps, that's easier to me. Some people say, that looks very complicated. But if you really break it down, it's not very complicated in terms of just straight calculations. Because it's three numbers. I mean, really, it's three numbers. It just looks like a lot. But because you are avoiding this part with using the percentage, but it's all the same. Okay? All right, so double I. If the volume of the water released measured at 22 degrees Celsius, calculate the volume of the water release measured at 22 degrees Celsius and 735 millimeters of mercury. Now, this one's going to get some of you. I need a volume, correct? Okay. What unit am I really going to want to be looking for? So liters or milliliters. So let's think about it for just a second. I've got a mass, I need a volume or milliliter, and I got a temperature, and what is mmHg? Millimeters of mercury. What type of measurement is that? It's a pressure unit. Now this is something we haven't covered yet, so I'm fishing for stuff right now. I've got a mass, I've got a volume, I've got a temperature, and I've got a pressure. Anybody? Well done, Trevor. I need Hibner. I need to know the answer to this question. It's not a big deal. I just need to know. How many of you have never seen that? I know I talked about it last year. Okay. So let's talk about what this stands for. First of all, the name of this thing is the ideal gas law. That's the name of this thing. Okay. P stands for what? Water. V stands for? N is the weird one. Thank you. N is equal to the number of moles. Don't fall for my trap. What is T? Temperature. Okay, not time, temperature. R is the odd one. I gave you guys at the very beginning of the year a formula sheet, correct? If you have that, please put your hands on it. On one of the sides, I don't know which side it's on, there should be some constants. I gave you one. It's got a bunch of equilibrium constants. Yeah. It's in there. Yeah, don't say anything out loud. I want everyone to put their eyes on it. Yeah, that thing right there. I want everyone to be able to put their eyes on it before you say anything out loud. Now, obviously, we're looking at R because that's what we're focusing on. On that sheet, you should have 3 values of R, true or false. Don't say anything. Nope. I want everyone to put their eyes on it. You should have 3 values of R. Do the numbers change? What else changes about the R's? Okay, so I know one, and I don't know what order they're in, but I know them. One of them is 8.31. It doesn't matter, but for your sake. One of them, what's the last number? 0.0821. That's right. Just for your purposes, because y'all are too anal to get over it right now. No. Y'all are just way too anal for normal human beings. All right, and then what's the last one? I don't even know what it is. What? Liters times torr. Madison, will you hand it to me? I'm tethered, so I can't hurt myself. Now, here's the deal. These are your 3 R's. Which one of them can you automatically eliminate? Wine. It's energy. Fantastic. This is my energy R. Okay, it's on there. Look at it. Mason, I can assure you by the end of the year you will know what joules means. So, that's my energy one. We're not talking about energy. So you can completely eliminate that from your discussion. Now, the bottom 2 are fairly similar, aren't they? Okay. The only difference, yes ma'am. A what? For who? We don't have any yet. We're still waiting on him. Where's he going? Okay. We're going to talk about that for a second. Chill out, guys. Chill out. Chill out. So, we've got 2 different things, and the values are drastically different. When we talk about pressure, we've got several different units of pressure, and we're going to get to all of these later. But I'm going to go ahead and throw them at you now. Now, my first question, and this is important that you know that. What causes pressure? What's the cause of it? Now, molecules are fine, but could you also say atoms? Yeah, that's why I write the word particles, because molecules are also particles. So it's important we understand this. So pressure is caused by collisions. And we'll get way more in depth of what collisions mean. We talked about the theory of something. I can't remember what it is. So there's major ones. We have ATMs, which stands for what? Atmospheres. We have MMHG, which stands for what? Millimeters of mercury. We also have torr. And the last one we have is PA, which stands for a Pascal. We'll talk about that later. Now, here is the coolest part of this. Stop. Here's the coolest part of this. That is the important part. The millimeters of mercury and torr are the exact same thing. Here's why. You should remember this. Oh, my kids should. From last year, the first chapter we ever did, we talked about pressure. We talked about Evangelista Torricelli. He invented the barometer. With the barometer, what he did is he took a petri dish full of this stuff. What he did is he had a test tube. Now, you tell me. I don't care. What he did is he allowed the atmospheric pressure to push on that mercury. If you push down on a liquid, where's the only place it can go? Up. So what happened is this tube filled with mercury. And guess how far that mercury moved? So, Torricelli used millimeters of mercury. That's why they're equivalent. Now, I know you want to kick the person and said, let's give it two different units that mean the same thing. It doesn't make logical sense. I agree with you. But the fact is that you have to deal with the garbage that we get thrown with. Okay, hold on. So, the important part is that I need you to know that enormous fact is that these two things are identical. Now, we know that Torricelli measured 760. But how much atmospheric pressure was pushing down? 1. So 1 atmosphere of pressure moves mercury how far? 760 millimeters. And who discovered that? Torricelli. Okay? Now, we're going to talk about pascals later. We don't even need to worry about it. And the reason why right now I don't care about that is because is Pascal anywhere in this R unit? So let me ask you something. Now let's go back to our original question. That's not the original. Yeah, it is. We gave a mass, a temperature, and a pressure, and we're looking for a volume. So if we come back here, can we rearrange this and we know we are solving for V? True or false? True. Isolate V from your ideal gas law. Okay, NERT over P. Now, very simple. The most challenging part that people are going to miss. What specific thing are we trying to solve the volume for? No, the water. That's the important aspect about this, because guess what you're going to want to do? Do you see that 3.21 grams of the hydrate? Can you convert that 3.21 grams of hydrate and plug it in as your number of moles? No. When you're comparing volumes to moles, you must use the same compound. So what are we trying to do? We need moles of what? Moles of water. That is the number one most missed thing about this problem. Over time, I can assure you, this whole issue with knowing which pressure unit and which R unit to use, that'll go away because of repetition. Knowing to convert the grams of the hydrate to the moles of water, that's the part where there seems to be an issue. Okay? Justin, go ahead. Okay? So, let me go back and let's look at this. If we have 3.21 grams of this whole entire thing, can we stoich it to get to moles of water? Yes. What's your mole to mole ratio here? 1 to 3. So would you agree we divide the hydrate by its molar mass of 151.08? Then what would you do with the 3? Multiply it by 3. So Justin, give me that value. We only stayed, we went to the beryllium oxalate. This time we're going to water. Okay, Justin, tell me what it is again. 0.191 moles of H2O. Now I'm going to skip R for just a second. Okay, go ahead. Okay. True. Moving. Okay. So 151.08, 1 to 3. All I did was just stoic through that. Does that help? Okay. got a few more. Let me finish this up, and I'm gonna leave you on a cliffhanger. Okay. So coming, it's the wrong answer. So, what is it? 0.0637. Okay. Now, here's the deal. We've got an R, we got a T, and then we've got a P. Do you agree that we have to use one of the R values? Let's look at the easy one first. We know we're not going to use the top one, but we're looking at the last two. Let's look at the temperature unit first. What is the temperature unit given in the question? Celsius. Is that a problem with both of these R's? Because do they have to cancel? They have to, because we're trying to find volume. Can you have the temperature unit left? We got to get rid of it, right? How do you convert Celsius to Kelvin? Okay. If you do not know that, if we need Kelvin, it's degrees Celsius plus 273. So what is 220 plus 273? 493 Kelvin. That's our temperature, right? Okay, so let's go back and let's plug in our temperature. So 493 Kelvin. So the last two things that we're missing are our R, which is a constant. Can you use that sheet on the exam and the test? Yes. And the pressure unit. Look at the question. What pressure unit is given? Millimeters of mercury. This is where your brain has to kick into overdrive. We've got 2 R's left. Do you see mmHg anywhere? Bingo. That's where your brain has to make the connection. That torr and mmHg are what? The exact same. I do use ATM in the video, but I'm explaining to you that if you want to use the bottom one, you can. But if you want to use ATM, what must you have to do to the millimeters of mercury? Convert it to atmospheres. That's an additional step that could cause you an issue. Instead of just plugging it in based on what we know, and reducing the number of calculations, there's a greater chance of making less mistakes. So that's the problem that the AP does. They rarely use the unit torr in a problem, but they use millimeters of mercury all the time. And if you know that torr is millimeters of mercury, you eliminate a whole step. Does that make sense? So we use which one for simplicity? The bottom one. You can, absolutely. But you would have to write it as 1 ATM. Okay? You can't plug in 760 mmHg for the pressure and plug in the liters over atmosphere unit. That doesn't work. The units have to make sure they cancel. Okay? All right, so we'll pick up here tomorrow and we'll re-hit it.